Section 2.2, Describing Sets. In this section, we're going to focus on Venn diagrams and the language that we use when using Venn diagrams to solve problems. First, let's start by talking about sets. Sets are groups of objects. We call objects elements. And they can be anything ranging from colors, numbers, people, days, any object that you could group together, we can make a set of that object. A finite list of objects, we can count how many things are in there. For example, in the set C that we have on the screen, we have red, green, yellow, blue are all in that set. I can count that there are 4 colors in that set. So there is a finite list for that set. An infinite list is something that just keeps going continuously, but because there's a pattern, we can see what the elements will look like. For example, the set N, which stands for natural numbers, those are our counting numbers, like 1, 2, 3, 4. And even though I'm not listing 5, 6, 7, 8, I'm using these 3 little dots to say the rest of the counting numbers belong to this set as well, but because the list is never ending, I couldn't possibly write them all down. Finite sets versus infinite sets. Finite sets can be very large. I can have hundreds of thousands of millions of billions of objects in my set, but as long as I can say that there is a definite stop number, like I can count them all, even if it takes me a lifetime, we'd call it finite. An infinite set, it might look small. 1, 2, 3, 4, that's not very big, but those 3 ellipse dots tell us that it's so big, we're not even going to bother writing the rest of it out because it will literally never end. We can list our sets by showing the elements that are in them, or we can use something called set builder notation, which tells you the rules for anything that will belong to a set. For example, on the screen here we have set builder notation, which describes a set with elements called X. And each of the elements have to follow the rule that is written after the vertical bar. That vertical bar, we like to say that that represents the phrase such that. And then everything that follows after that is the rule your elements will follow. So we could read this as, this set contains elements X such that X has to belong to the natural numbers, so X with this symbol followed by the letter N, we read that as X belongs to the set of natural numbers. There's a second part of the rule that says that X also has to be smaller than 5. So the elements of this set have to follow 2 rules. Not only do our elements need to be natural numbers, they also need to be less than 5. So maybe I list out some of my natural numbers. That's good. And then I want to think about which of these natural numbers are smaller than 5. Notice that this says X is less than 5, not equal to 5. So I would not be able to include 5, or 6, or 7, or 8, or 9, or 10. This set, X, such that X is an element of the natural numbers, as well as X is smaller than 5, that's simply the set containing the numbers 1, 2, 3, and 4. Now that might feel like overkill, set builder notation for a set that just has the elements 1, 2, 3, 4, and you're right. This is just a simple example to show you how set builder notation works. But when we start to talk about sets that have more complicated rules, it can be much easier to write out set builder notation than it is to try and list all of the elements. Let's practice using some set builder notation. So for this first set, I see we have the elements 2, 4, 6, 8, 10, and then the 3 dots telling me that this pattern continues. And hopefully we can tell that these are all even numbers and positive. So if we wanted to write this in set builder notation, we might start with something like the elements, maybe we call them E for even. We can use whatever letter we like, such that E is even, E is positive. And you can use phrases to describe the rules that the set has to follow, or we can try to come up with mathematical expressions that say those same things. Now think about all even numbers. Even numbers all can be divided by 2, and that's because any even number is literally a multiple of 2. It's 2 times something. 16 is even, it's 2 times 8. So an even number can actually be written as 2 times n, where n is an element of the natural numbers. So instead of writing n as even, we could write set builder notation to say E is equal to 2 times n. And then we also want to incorporate that it's positive. Natural numbers are only positive, they don't include negatives, so that actually incorporates both rules into one short expression. We just need to finish this by saying that n, which we're using to define E, belongs to the natural numbers. Let's try another set. We have 1, 3, 5, 7, and then the 3 dots to say it continues. These look like all odd positive numbers. So we can do the same thing we did last time. Maybe we call them O for odd, such that O is odd, O is positive. And if we'd like, we can try making a mathematical expression. Instead of writing our rules in words, we can try finding an expression that shows the rule. If any number 2 times n results in an even number, we can always add 1 to an even number to make it odd. Think of any even number, add 1 to it, and then now you have an odd number. So an odd number is simply an even number plus 1. And again, we're using natural numbers for n. That way we are not including negatives here. Now I will make a recommendation. I used O for odd, but O happens to look a lot like a 0. And 0 equals 2n plus 1 is not what we're going for. So maybe instead of using O, we use something that's a little less descriptive, but easier to not confuse. So I'm going to replace all of my O's with X's. It's nice to use letters that are related to the problem that you're working with, but sometimes it just doesn't work out so well. Oh, I noticed a tiny hiccup here. I'm using 2n plus 1 to make odd numbers, which is true. But if I start with my first natural number, where n is equal to 1, that's the first natural number, then the first odd number that I get is 2 times 1 plus 1, which is 3. And my set contains the element 1, so I need to find a way to make an odd number so that when I plug in my first natural number, the number 1 comes out rather than 3. And we can make that correction real quick. All we need to do is switch our positive between the 2n and the 1. Let's make that a minus. If we have 2n minus 1 and we plug in our first natural number, 1, then 2n minus 1 becomes 2 minus 1, or 1. So we can fix that in our set builder notation as well. That should be a minus. Oh, I have more on the slide, but I can't see it. Let me clean it off. Let's try going in the reverse order. In the first two examples, we took a set that was written as a list and we converted it into set builder notation. And these examples, we're going to take a set that's in set builder notation and we're going to rewrite it with a list of all of the elements. This set A, the elements look like 2k plus 1, such that the rule that they follow is k has to be 3, 4, or 5. So what we're going to do is find out what 2k plus 1 looks like for each value of k. So if k is equal to 3, then 2k plus 1 looks like 2 times 3 plus 1, which is 7. If k is equal to 4, then 2k plus 1 looks like 2 times 4 plus 1, which is 8 plus 1, or 9. And then lastly, we have k equals 5. If that's the value of k, then 2k plus 1 becomes 2 times 5 plus 1, or 10 plus 1, which is 11. So this set A is going to contain the elements 7, 9, 11. What about the set B? The set B says the elements are called x such that x is a positive, even, natural number less than 8. Now here we don't have an equation to work out, but we could list out the positive, even, natural numbers that are less than 8. So we would start with positive numbers. 0 is not positive or negative, so we won't use that. Start with 1. 1 is a natural number and it's less than 8. How about 2? Yep, 2 is positive, it's a natural number, it's less than 8. So is 3, 4, 5, 6, 7, and that's it. Because 8, although it's positive and a natural number, 8 is not less than 8. So the set B, written out as a list, looks like the set 1, 2, 3, 4, 5, 6, 7. I have a couple things to add with our set builder notations, and that is that the order of your elements does not matter. In each of these examples, we used an order that went from small to big, but that doesn't have to be the case. For example, the set A of 7, 9, and 11, there's no reason that we can't write it 9, 7, and 11. Or we could have even mixed it up differently to say 11, 7, 9. These are all the same exact sets, they're just written in different orders. So order is not important in set notation, although conventionally we like to go from small to big. Also, we will never repeat an element in a set. If I were going to list off numbers, people's favorite numbers, for example. If we were in class, I could ask everybody, write down your favorite number. If you don't have one, just make one up. And then we could list out all of the numbers in class, and let's say maybe to make it easy, there's 5 students, and one person picks 7, one person picks 13, another picks 7, 11, and 0. If these were all the favorite numbers that the 5 students picked, and we wanted to make a set of those, F for favorite numbers, I wouldn't write 7 twice. I only need to write it once. Although it appears twice for what people picked, I would only write it once because we don't repeat any elements in a set. So a set is not trying to tell you a list of everything that exists. They're just showing you all of the different options that could exist in the list. That brings up the idea of equal sets or equivalent sets. 2 sets are considered equal if they have the exact same elements. 2 sets are considered equivalent, but not equal, if they have the same number of elements, but their elements are different. So looking at the sets that we have on the screen, we have A, which includes the letters P, Q, R, and S. We also have the set B, which includes A, B, and C. We have the set C, which includes X, Y, and Z. And we have the set D, which includes D, A, and C. I said D. D includes B. Careful, I just switched my letters. The set D includes B, A, and C. If we're looking at these, and we remember that the order of elements is unimportant, then we can see that a couple of these sets are identical, they've just been shifted around and renamed. So we would like to identify any sets that are equal and any sets that are equivalent. So if we take a look at the set A, we can see that there are 4 elements, and the elements are P, Q, R, and S. Looking at set B, B only has 3 elements, so A and B are not equivalent. If they're not equivalent, they definitely can't be equal. So A has 4 elements, B has 3 elements. A and B are not equivalent, they are not equal. We can write that as A is not equivalent to B, or A is not equal to B. The same is true for A compared with C and A compared with D. So we can tell that A is kind of an outsider. It's got more elements than anybody else, so therefore it's not equivalent and it's not equal. If we look at the set B, we see that there are 3 elements. There's 2 other sets in this list that have 3 elements. The set C has 3 elements, which means B is equivalent to C, and the set D has 3 elements, so the set B is equivalent to D. Now, if we wanted to talk about equality, we need to compare all of the elements in B to all of the elements in C. And we've got completely different letters there, so we can tell B is not equal to C. But if we look at the set D, notice that both B and D have A, both B and D have B, and both B and D have C. So B is equal to the set D. So far we've got 2 equivalence statements, true equivalence, and 1 equality. And let's keep going down the list. If we look at the set C, C has 3 elements, therefore C is equivalent to both B and D. So we have C is equivalent to B. We already have that here. C is equivalent to D. Add that to our list. Is C equal to anybody else? No, because no other sets contain X, Y, or Z. And then if we go down to the set D, well, we've compared D to everybody else. We know that D is equivalent to B. We know D is equivalent to C. We also know that D and B are equal. So these are the equivalent sets, and this is the equal pair of sets. A one-to-one correspondence is basically a way of saying that you can pair up the elements that belong to 2 different sets. So let's think about the set A that contains the elements 1, 2, and 3. And let's consider the set B, which contains the elements A, B, C. A one-to-one correspondence says that I can take an element from set A and I can pair it up with an element from set B. So I could easily pair these in the order that they're already written. This would be one of the one-to-one correspondence. But there's no reason that I have to have it ordered this way. Maybe instead of doing it straight down, maybe I go at a diagonal where 1 pairs with B, 2 pairs with C, and then 3 would have to pair with A. I still have a partner for every element in the set A to be paired up with an element from the set B. And maybe I take it a little further and I do 1 to C, and then 2 to A, and then 3 to B. We can make a lot of different pairings. If two sets can be written as a one-to-one correspondence, then they have to be considered equivalent. If I need a partner for every element in set A, and I get to use the elements in set B, then they have to have equal numbers of elements, otherwise somebody would be left without a partner. There are so many different one-to-one correspondence arrangements that we might wonder, how could we possibly find how many of these different arrangements exist? Now, the shortcut doesn't always tell you exactly how many, it tells you how many, but it doesn't tell you what the one-to-one correspondence is. So sometimes we just want to know how many different ways can I pair these elements up, and that's what we're going to talk about here. How many one-to-one correspondences exist between two sets? And what we'll use to answer this question is something called the fundamental counting principle. It's a way to count things very quickly without having to go through all of the possible combinations. Think back to when we were doing truth tables and we wanted to think about all the possible combinations of two statements where we have true and false. We had to list all of those out. And if we forgot to list one of the options, then we maybe missed out on a possibility of a truth statement. So this is going to help us count all of the ways that we could pair things together. The fundamental counting principle says that if you have some event M, which can occur in so many ways, I'm going to use uppercase M to represent the event, lowercase m to represent how many ways that event can occur. And then after that has occurred, we have the event N, so separate event, and that event can occur in some number of ways. I'll use uppercase N to talk about the event N, lowercase n to talk about how many ways it could happen. Then, if M happens, and then immediately after that N happens, we can count how many ways that those two events could happen in sequence simply by multiplying the number of ways M could happen to the number of ways N could happen. So little m times little n, we could look at that as the number of ways the first event happens times n, which is the number of ways the second event happens. So if we wanted to count up all the one-to-one correspondences between the sets A and B, what we need to do is think about how we're pairing the elements. So let's think about the set A, which has elements 1, 2, and 3. Element 1 needs a partner. So a partner for 1, that we're going to call that event M. So picking a partner for 1, I have 3 choices for that. I could pick 1 to go with the element A, or I could pick 1 to go with the element B, or I could pick 1 to go with the element C. So the event M, a partner for 1, could happen, little m, 3 ways. Once I've picked a partner for 1, I can pick a partner for 2. Let's call that N. Now, hypothetically, let's say that we did pick an element for 1, and to make it simple, let's pretend that we picked A to be the partner for 1. Then when we look at a partner for 2, we only have choices B or C left. And it doesn't matter if A had been the partner for 1 or if B had. If 1 had been paired up with B, then when I go to pick my element to pair up with 2, I would only have A and C as my choices. So my point is that when we go to pick a partner for the element 2, one of the elements in B will have already been chosen, so there should only be 2 options left. So the event N, picking a partner for 2, can only happen in 2 separate ways. Therefore, if we want to know the number of ways that we can make a one-to-one correspondence between the sets A and B, we would multiply 3 times 2. Which means there are 6 different one-to-one correspondences that we can make, and I challenge you to see if you can make all of them. We've talked a bit about equivalent sets. Those are the sets that have the same number of elements. Well, when we talk about the number of elements a set has, that has a special name. It's called a cardinal number. So a cardinal number can be denoted as n with parentheses around the set name. So n parentheses set name. So if we're talking about the set S, the cardinal number of F's would be n parentheses S. And that just tells us how many sets are, or how many elements are within the set. So let's practice finding cardinal numbers. For this first set K, we have the elements 3, 5, 8, 0, 11. There are 5 elements in that set, so the cardinal number for K is 5. We write that in parentheses K is equal to 5. The set L, this is a set that contains the number 0. This can be confusing at times. 0 often makes us think that there's nothing in the set, but actually the number 0 is something. So the set L contains one element. The element is the number 0. Therefore, the cardinal number of L is equal to 1. I have one element in that set. The set X contains all of the elements such that they are a real number, and they satisfy this equation. X equals X plus 1. Now, we could try and guess a few values of X and check to see if they satisfy this equation, or we can think back to an algebra class that we've had in the past, and we can try to solve this equation for X. We would want to combine the X's on one side of the equal sign. Right now we have them on both sides. So I'll subtract X so that I can get rid of the X that's on the right. But look what happens. On the left, X minus X, I get 0. And on the right, I'm left with 1. But 0 is never equal to 1, so that tells me that this equation has no solutions. So this set is talking about elements that solve that equation. We just discovered that equation has no solutions, so the only thing that we can possibly conclude is that there's nothing inside of that set. We can call that an empty set. It's just a void space. There's nothing in there, like an empty box. The cardinal number of that set would be 0. There's nothing in the set, so we can't count how many things are there. It would have to be 0. The set Y is using a symbol that represents the empty set. So the symbol 0 with a slash through it, this is a symbol for the empty set. Y is equal to the empty set. This is just like the last set we looked at. There's nothing in there. It's empty. So the cardinal number of Y would also be 0. X and Y are both empty sets. They look very different the way that they're written, but they both have nothing inside of them, so their cardinal number has to be 0. Now we're going to get to the pictures, Venn diagrams. You might have seen these before when you're brainstorming ideas. We like to draw these big circle graphs to help organize our thoughts. We're going to break down some of the basic elements in this section for a Venn diagram, and then in the next section, we're going to talk about other properties and operations with sets. First, we're going to start with a universal set. That's what I'm representing here in this red rectangle. the universal set is supposed to contain everything in the universe, which is why it's named universal. So if I were to talk about people on the planet, that would be the universal set. Subset is a small group within the universal set U. So A is a subset. I'm representing that subset as a circle within the red rectangle. The universal set is all people on the planet. Maybe the subset A is students at Merced College. Anybody who's a student at Merced College lives within the universal set, therefore they belong to both groups. So if this dot inside of the circle A represents a student at Merced College, we can also with confidence say that that dot represents a person that lives on the planet. Anything outside of the circle A, but still within the rectangle for U, we call that the complement of the set A. That's saying everything that's outside of the subset A. And it might be a little hard to read, but the notation for that is the name of the set with a bar on top of it. That's the complement of the set A. That's everything outside of the circle A, but inside of the rectangle U. Let's try to use these diagrams to help us solve a problem. So I've copied everything onto this slide, and we've got sets here that have elements within them, and we're going to use this diagram to help us answer the questions. So U, the universal set, has the elements A, B, C, D. Now, if I jumped to conclusions, I would just write A, B, C, and D inside of the universal set. But maybe some of those elements belong to the subset, and I realize that I've called this B, so let's change that to A so it matches our diagram. So A, the subset, contains C and D. So I'm going to move the element C into the subset A. I'm not going to write it in both places because we don't repeat elements here. And then I'm going to do the same thing for D. I'll move D into the set A. Now I can see that if I were to ignore the subset circle A and ignore the complement A, if we were just in the universal set, I have A, B, C, and D. But then if we want to talk about the set A, I can see that the elements C and D are inside of that set. We're asked to find the complement of A, so that's everything that's not inside of the circle A, but still inside of the rectangle U. So the complement of A would be the elements A and B. Notice that A and B are not part of the set A. We're also supposed to find the complement of the universal set. Now, if the universal set includes A, B, C, and D, and we're saying that that's the entire universe, that's everything, then the complement of the universe would be nothing, emptiness. And if we wanted to find the complement of the empty set, so if the empty set contains nothing, the complement should be the opposite of that. That would contain everything, which would be the set U for the universe. Let's try another one. The universe set is an animal in the zoo. So we have all the animals in the zoo. And maybe we can think about some animals in the zoo, like a tiger, a bear, birds, snakes, anything you can think of, animals at the zoo. The set S, let's go ahead and rename that so that it matches our diagram. We'll call it set A. That contains a snake in the zoo. So I'm going to move snake, the set A. Now I can see that this universal set, which contains all animals in the zoo, we haven't removed anything from the universal set. We've just sorted it so that we can see that the snake belongs to the set A and everything else is outside of A. We want to describe the complement of A. Now we could list different animals, or we could just say the complement of A, we could use our set notation here, is an element X such that X is an animal in the zoo, but not a snake. There's different ways to word that same sentence. We could say it's any animal in the zoo, non-snake animals in the zoo, but you want to communicate the fact that it is an animal in the zoo, but it is also not a snake. So we have our universal set. We know what a subset looks like. It's a circle within the other set. We also know what a complement of a set looks like. But now we need to talk about something called a proper subset. Now, it's possible for a subset to be identical to the set that it's supposedly inside of. So we have to distinguish that two sets that are not equal, one of them could be a proper subset. If B is a subset of A, and B is not equal to A, what that means, if they're not equal, is that A has to have more elements in it than B does. I've got a little dot up here that says that this element belongs to A, but it is not inside of B. So that's how I can clarify that B is not simply just a subset, it's a proper subset. We use this little sideways cup notation to say that B is a subset of A. And I'd like for you to think of it kind of like an inequality. B is smaller than A. We know that it's smaller than A because A has elements in it that don't belong to B. But everything that's inside B is inside of A because it's drawn within the circle for A. Let's practice identifying subsets and proper subsets. We have three sets, A, B, and C, each one of them with their elements listed. We want to identify all the subsets relationships that occur among the sets. So subset means that they could be equal to each other or they could be smaller than. So let's start by looking at our sets. We have A with elements 1, 2, 3, 4, 5. We have B with elements 1 and 3. And we have the set C. Now C is in set builder notation, so we're going to have to do a little work to find out what those elements look like. We know that the elements follow the rule x equals 2 raised to the power of n minus 1. And n is any natural number. So let's start off with n equals 1, n equals 2, n equals 3, n equals 4. And it doesn't actually tell us when to stop. So we're going to just do a few of these. If n is equal to 1, then that element looks like 2 to the first power minus 1, which is just 2 minus 1, or 1. If n is equal to 2, that would look like 2 squared minus 1, which is 4 minus 1, or 3. If n is equal to 3, that would be 2 cubed minus 1. That's 8 minus 1, which is 7. If n is equal to 4, that would be 2 to the fourth power minus 1, which is 16 minus 1, which is 15. If n is 5, that would look like 2 to the fifth power minus 1. That would look like 32 minus 1, or 31. And we really don't have to go that far, because if we look at the other sets that we're comparing this set C to, the largest number in A is 5, the largest number in B is 3, so we really could have stopped at n equals 3. So let's just go from there. And we'll write out that this is a list that continues. So our list contains 1, 3, 7, etc. Now we're ready to try maybe a diagram. If we let the set A have 1, 2, 3, 4, and 5 in it, notice that we can draw a circle around the elements 1 and 3 and call that the set B. There are elements outside of B that are still inside of A, so B is a proper subset of A. Part B is asking us for proper subsets, so we can write that down here. We can also write that B is a subset of A, but not proper if we weren't sure, by underlining that subset symbol. That's saying it's possible for B and A to be equal to each other. Let's check and see if we can circle elements from the set A to make the set C. Well, we have 1, 3, but no 7. So if we wanted to draw a circle for C, it would have to be outside of A. The circle C would need to have the 7 added to it. So because there's an element in C that does not belong to A, and there's elements in A that do not belong to C, these are not subsets. So C is not a subset of A, and A is not a subset of C. We've compared A to both B and C. Now let's compare B and C. So if I draw the circle for B, then we have 1 and 3 inside of this circle. And if I tried to circle the elements for C, I would notice that I'm missing a 7 again. So I'd have to draw a circle that goes outside of B so that I could put a 7 in it. Notice here that the circle B outside of C, so this whole area, it's empty. So we could draw this same picture with C being the larger circle with 1, 3, and 7 in it, and then B exists inside of C. So that tells us that B is definitely a subset of C, but also that B is a proper subset of C, because the element 7 is inside of the set C, but not inside of the set B. So we're using Venn diagrams here to see the relationships between the two sets.